Hello everyone, welcome back to Advent Code 2020. We're going to do day 10 today, sort of. I started recording this a while ago, and I got like most of the way through when I realized that I had at some point accidentally pressed the stop recording button and didn't notice because it's kind of small, the thing that indicates whether I'm recording or not, and it's not usually what I'm looking at. So instead, I'm just going to read you guys the problem and then walk you through my solution and how I got there. We're not going to be solving this one live today. But, it didn't take me that long. Less than an hour for sure. I found this problem easier than most of the recent ones. Anyway, let's get started. Day 10, Adapter Array. Patched into the aircraft's data port, you discover weather forecasts of a massive tropical storm. Before you can figure out whether it will impact your vacation plans, however, your device suddenly turns off. Its battery is dead. It's kind of remarkable, isn't it? Like how prepared we are for all kinds of outrageous circumstances. Oh yeah, of course. I've got a thing here that fixes people's PlayStation, Nintendo Switches, or whatever. I'm like, oh yeah, I guess a battery for my thing. Didn't think of that. Anyway, you'll need to plug it in. There's only one problem. The charging outlet near your seat produces the wrong number of jolts. Always prepared, you make a list of all the joltage adapters in your bag. Each of your joltage adapters is rated for a specific output joltage. Any given adapter can take an input 1, 2, or 3 jolts lower than its rating and still produce its rated output joltage, which, by the way, seems like magic. In addition, your device has a built-in joltage adapter rated for 3 jolts higher than the highest rated adapter in your bag. So we want to get, we need to use our last adapter, is kind of the requirement there. Treat the charging outlet near your seat as having an effective joltage rating of 0. Since you have some time to kill, you might as well test all of your adapters. Wouldn't want to get to your resort and realize you can't even charge your device. If you use every adapter in your bag at once, what is the distribution of joltage differences between the charging outlet, the adapters, and your device? So for example here, if we were working on this, we would start at 0, and to use them all, it means you just have to arrange them in a sorted order. Because you can't ever go from a higher number to a smaller number. That's not how these adapters work. And we need to use them all, which means we need to do them in order. So we'd go from 0 to 1 to 4 to 5 to 6 to 7 to 10 to 11 to 12 to 15, 16, 19, and then 22, which is our actual device. And so what they're asking us to compute then is the sum of the differences between adjacent elements in our list. And in particular, they only care about 1 and 3 jolt differences for some reason. There won't be any 2s, or at any rate, they don't care about 2s. So what they're asking is, find a chain that uses all of your adapters to connect the outlet to your device's built-in adapter and count the joltage difference between the outlet, the adapters, and your device. What is the number of 1 jolt differences multiplied by the number of 3 jolt differences? Now, I don't know whether our input has any 2 jolt differences, but we can just ignore them. So here's where we look at the implementation. All these imports are just for part 2. Actually, data list we needed for part 1. I actually wrote part 1 just all by itself here because this seemed like a pretty simple problem. I did get something wrong once or twice here. Maybe just once, actually. I think I forgot the 0. Yeah, that's what it was. But this is just... None of these functions are really exciting enough that they need a name. It might be interesting to, extract out names for some subpieces of these as just, their own compositions and just, give them a name for clarity. But as for wiring them together, I thought it was more useful to just, think of the data pipeline. And the algorithm that I had in mind was okay, as I said, you just have to sort them and compute the pairwise differences. How hard could it be? So first we add a 0. That's the power source. And we could, at this point, add something that is 3 greater than the largest one. But instead, it turns out to be simpler to just compute all the differences and then add a 3 to that result. Because we know what the difference will be. It's defined by its difference, not by its value. So anyway, we add a 0, and then we sort them so we have them in order. And then we use this zip width to compute the pairwise difference of elements. Normally you would just zip width minus to compute the pairwise difference, but in this case our list is in ascending order. So we want to flip minus. And this is the same trick we've seen before of zip times tail here, or whatever you're supposed to call this function, app, I don't know. Where we call this zip width flip minus with this using the applicative instance for functions gives you back a function that takes a list, calls this on that list, and also calls this on that list, and then calls the function it got here on the value it got here. So we're zipping the list with its tail using a flipped subtraction operator. That gets us the pairwise differences. Then we throw out everything that isn't 1 or 3. There should only be 2s, maybe none. I don't know. And we add 1, 3. This is the final jump from the last adapter to the device. And then we sort this again so that we can group them into partitions equal to 1 and equal to 3. And then we actually just throw away the 1s and 3s themselves and keep only the lengths. And multiply that all together, and you get a product. And this works. We got an answer of 2,760. So, part 2. To completely determine whether you have enough adapters, you'll need to figure out how many different ways they can be arranged. Every arrangement needs to connect the charging outlet to your device. The previous rules about when adapters can successfully connect still apply. And then they give us some examples. These are all successful ways to get from 0 to 22. And you're meant to count the number of legal ways there are to do this. And then they give, for the bigger example, there's many, many arrangements. Here are a few. You glance down at your bag and try to remember why you brought so many adapters. There must be more than 1 trillion valid ways to arrange them. Surely there must be an efficient way to count the arrangements. And indeed, our input has, I believe, 109? 108. 108 values in it. So there are roughly, well, there are exactly 2 to the 108 possible sets of adapters we could use, which is like extremely large. More than 1 trillion is underselling it by a lot. Right, because 2 to the 10 is 1,000, 20 is 1,000,000, 30 is 1,000,000,000, 40 is 1 trillion. So there's like a quadrillion ways you could do this. So any algorithm that kind of is just an optimization of doing the dumb power set idea is doomed. Right? You could like arrange. You could explore the power set somewhat more efficiently by saying, okay, well, like rather than just choosing every possible set of adapters and seeing does this work, you could say let's start with all the adapters and then try removing one of them. And if it's invalid, then you can just throw away every set that doesn't include that one. And if it is valid, then you can continue exploring all the things you could explore. All the ways you could either remove that one or don't remove that one. But that still leads to many, many adapters, I think. I didn't try it, but it just seems like it would be very, very expensive. So I've spent some time thinking about a more efficient way to do it. Not too long, just a few minutes. And I decided that what we have, let's go back and look at the problem, actually. What we have is kind of a dynamic programming approach that should work fine. Much like we did yesterday. Although, it must be said, I talked to someone about like the smarter algorithm that I thought about using and tried to use but did it wrong. And I wasn't sure whether it would, in yesterday's problem, right? And I wasn't sure whether it would work, whether you could prove that it was correct, or whether there were counterexamples where it wouldn't apply. And it actually is correct. The proof is sort of interesting. Maybe since I'm doing a short episode today, we'll go back and look at that. That'd be kind of fun. Anyway, but dynamic programming. So our goal is to look up how do you get to 22. But let's imagine for a moment that our goal was just to get to 7. Ignore all this other stuff. We want a very small input set that we can do by hand. How do we find this out? Well, the number of valid ways to get to 7 is just the number of ways to get to 6 plus the number of ways to get to 5 plus the number of ways to get to 4. Right? Because you can jump up by 1, 2, or 3. All right. Well, how do you get to 6? Well, it's the number of valid ways to get to 5 plus the number of valid ways to get to 4 plus the number of valid ways to get to 3. And so you can see already there's some duplication. We're looking at 5 and 4 twice. All right, well, how do you get to 5? The number of ways to get to 4 plus the number of ways to get to 3 plus the number of ways to get to 2. And so on. So there's all this reused work. And so what we'd like to do is build a table where we store a result once we've used it once. And that way we can reuse it in the future. And so in this way, we're doing only a linear amount of work instead of an exponential amount of work, which is obviously a big improvement. Right? To compute any particular number, we just do 3 table lookups and then add some stuff together. 3 numbers. So that was what I decided to implement. And I ended up using an int map because we're storing a map from int to int, so it makes sense. An array, again, would be fine, or a vector, but like, as I mentioned previously, vectors and arrays are just too hard in Haskell. I don't use them. I ended up needing a set as well, because here's my part 2 solution. And this one I needed to refine a couple times. I did get it wrong here and there. I have these type annotations in because I had the type wrong somewhere. It was because I forgot to put the key in when I was building a list. And it inferred types for solve that solve must return a tuple, it thought, when I had written just solve x here instead of x. So the idea, the kind of core algorithm is here in solve, and the rest of it is like building up to that. Where we have solve, we say, how many ways are there to get to the number x? Well, to get to 0, there's a single way, 1. That's our base case. Otherwise, if S is one of the adapters we have, then look up in our table x minus 3, x minus 2, and x minus 1. However, if x is not in our table, don't bother looking anything up. It's impossible to get there ever, because you just don't have that adapter. And that's kind of it. The rest is like, okay, well, we have to build a set from the list of adapters because we want to be able to quickly query whether we have such an adapter. And we need to compute the goal, which is to get to the largest one plus 3. And so sets use a tree underneath, so they have find max to tell you I lost, my brain fell out. To find the maximum element, and then we just add 3 of that. And then we have this thing available, which is whether it is possible to get to that voltage, or whether it might be possible. Actually, whether it is, because we know it's possible to use every adapter. That was what part 1 had us test. So we just add to our inputs the goal, because we also want it to be possible to get to the goal. And then we just build a table where we say for each x, solve for that x. And you actually have to start at minus 2, because otherwise when you try to solve 1, it says, oh, let me look up in the table what 1 minus 3 is. And we just have to say, no, that's not allowed. We have to say, yes, go ahead and cache that value. We could have enhanced solve to handle, like, if x is less than 0, it's 0. But I don't know, it just seemed fine to put it into the map. Why not? And this is the whole problem. And this works, and it runs, and we get like a very large number, right? Million, 6 billion, 13 trillion, just counting the valid ways, not counting the invalid ways. So there really are quite a lot. Okay, so let's actually talk now about, as I said I might, about yesterday's puzzle. About the algorithm I thought of using but wasn't sure it would be correct. You need to find a contiguous set of at least two numbers which sum to the invalid number from step 1. And for the purposes of this discussion, it doesn't really matter what the invalid number was. We just need to find a contiguous set of at least two numbers which sum to this invalid number. And the algorithm that I had in mind, and that I wasn't sure was correct, was to start with a range like this, and if it's too small, expand it forward until it gets too large, and then contract it backwards until it's no longer too large. And I wasn't sure, like there are a number of summations this isn't including, right? And I couldn't see how to prove that none of those are the one we're looking for. But it was explained to me that this algorithm seems like it should work anyway. It wasn't a rigorous proof, but it was like, a couple paragraphs of why it should work. And I looked at it and I said, yep, that's right, I believe it. And so the argument is, let me go look at this in Emacs actually, so that so I have a better text cursor. Suppose that we were, let's define three numbers, S, N, and M. S is the sum that we're looking for, and N and M are the indices, the start and end index of the range that sums to that number in our list. We don't know what N and M are, those are what we're looking for, but we know what S is. So suppose we had this, right? Suppose this was our S, and it's 174797, right? In this case, our N would be 3, happens to be the one at the third index. Not that it happens to also have value 3, which is just a tremendous coincidence, but and our M would be 6, index pointing to 50. And the argument that was given to me that convinced me is you will certainly eventually include N in a range, in some range, right? Because you're going to be searching through the entire list, and eventually N will enter your range, right? Because you won't have found your sum by then, since it starts at N, not ends at it, and you keep going until you have gotten to N event, until you include it in the range eventually. And of course, at some point, it'll be like this. We'll have it at the end, not the beginning, but it'll be in our range. So you'll have N in your range eventually, and it won't ever leave your range except as the last element, right? We'll never do this and then say I don't want to look at 3. Let's just look at 17, 27, and 14. The only way anything ever leaves the range you're looking at is via the top here, the N. And so eventually we will be looking at some range where N is at the beginning of it, and some more numbers follow, right? And if those numbers are too large, well, that's impossible, because that means we've gone past a set that... So, okay. Yeah, I guess this is a thing to point out. Will our range ever go past M without finding the answer? And the answer is no, because our range already includes n, and because n hasn't dropped out yet by the time we get to m, and we can't have gone past m, or else we would have stopped before that, right? So at some point we'll get to a point where m is at the top of the list. And we won't have thrown away n yet, because if we look at all the subsequences leading up to m, they're all too small. And so if we ever looked at this, we would make it bigger. If we looked at this, we'd make it bigger, not smaller, right? Making it smaller like this would be incorrect, because this region is not large enough. We need more, not less. We would expand it, and we eventually get to m. So that was like roughly the algorithm, or the proof that was explained to me and that I found convincing. Okay, there you go. So, sorry you guys didn't get to see it live today, but I hope that the algorithm was interesting to you, and also this immense pile of point-free soup was at least amusing. Hope you guys enjoyed. Thanks for watching, and I'll see you next time.